Tech-ni-shn here again. Today I will be looking at the RF preamp, and the device I'm using is the BFQ19. I'll be looking at gain, return loss, intermodulation and noise figure. The PCB I'm using can be rewired so it is switched to operate in both directions. The relay switching is made separate from the amplifier DC input. Additionally, the collector base feedback comes directly from the collector rather than via the output transformer. This improves the stability. I've set the components so that the gain of the amplifier is a nominal 15 dB. There is a 5 dB attenuator fitted to the board, so the overall gain is approximately 10 dB. The attenuator provides a good termination when the amplifier operates in both directions. The 2N5109 is obsolete, as are similar devices, so unless one has existing stock, then the amplifiers are hard to build. Counterfeit devices are commonly available, but they don't show the same performance. SMD devices are more prevalent now, so I decided to try one in the same PCB as the IF amplifier tested earlier. I selected the BFQ19 as being a current device and still on the active list. It is available from DigiKey, Mauser and similar suppliers. The full part number is shown at the top of the screen. This device is rated about 1 watt, and I will try to keep the dissipation to about half a watt. In fact, the dissipation in this amplifier is approximately 0.25 watts or a quarter of a watt. The FT of the device is in the gigahertz region, approximately 5.5 gigahertz. And during testing it was unstable, probably due to the existing layout and due to reactances. Some circuitry was needed to improve the stability, and they've been done on the board above the changes that were introduced in the 2N5109 PCB for the IF. One of the changes was to provide a high frequency termination for the collector. The transformer provides a good termination at HF and low VHF frequencies, but is probably an unknown quantity at UHF and microwave frequencies. So by adding a termination, high frequency termination on the PCB, it improved the stability. What I used was a 100 ohm and a 4.7 picofarad from the collector to ground. These two components were in series. Additionally, track length is important, and a reduction of track length was done in the emitter circuit. In the end of this section of the video, there will be a couple of pictures which will show what I have done. The equipment used, as I have used previously, is the Siglent SSA 3021X spectrum analyzer, attenuator, the Rigol DG1062Z, signal generator, combiner, miscellaneous coax cables and adapters and terminations. The setup below is for measuring gain. I have fitted a 10 dB attenuator between the spectrum analyzer output, tracking generator output, and the input to the RF amplifier. The output of the RF amplifier goes back to the spectrum analyzer input. The picture shown on the screen is the setup for looking at return loss. I can change the direction of the RF amplifier by activating the relay, so we can look at both the input return loss and the output return loss. I'll be checking for intermodulation, and the mixer input intercept was about plus 25, so I would hope that the output intercept of the BFQ19 RF amplifier is in the region of 5 dB above that, or plus 30 dBm. So the overall IP3 isn't degraded any further except for the gain. Note the overall intercept performance is degraded slightly by the IF preamp, as that is the weakest stage overall. I can do the intermodulation test in two ways. The first way is using both outputs of the DDS generator and then combining them, or I can use the one output and go into a double sideband suppressed carrier mode, and I'll be using that to check the intermodulation performance. I'll check the performance at three frequencies: at 4 megahertz, approximately 80 meters; at 14 megahertz, approximately 20 meters; and at 28 megahertz, approximately 10 meters. The figures shown on the screen were very close to what I measured, and that is a good result. This is the first setup for checking the intermodulation using both outputs of the dual DDS generator into a combiner, a 10 dB attenuator, and then into the amplifier, and then into the spectrum analyzer. Point to note is I have found on a number of occasions that adding extra attenuation above the automatic attenuation of the spectrum analyzer does improve the IMD results. So the existing attenuation settings are not quite ideal on the spectrum analyzer. This is the second setup for looking at the intermodulation. I will set the output of the RF amplifier to be 0 dBm into the spectrum analyzer. Noise figure tests are done at the three frequencies. When I do the gain test, I'll write down the gain figures for the three frequencies, as I'll need to use them again for the tests. When I was checking for spurious before in the early tests, I used my Tech-ni-shn Ultra, and I saw spurious signals in the region of 2 gigahertz. Then by doing the changes, I made the amplifier stable. Right, this is a picture of the board, the underneath of the board. The yellow marks on the screen are where the tracks are cut, and the red trace, the X, is cross wires. This enables the output of the amplifier and the input amplifier to be swapped over when one turns the relay on and off. The cut down below at the bottom of the screen is to disconnect the resistor network going to the base from the tap of the transformer and make it come from the collector of the transformer directly. This improves the stability of the amplifier. Right, this is the top of the board. The cut on the right of the screen is to separate the relay control from the power going to the amplifier. I use the connections of D1 there to introduce the volts to the amplifier, and what I have done in the past is I fit a diode bent over radially so the cathode lead goes to the relay, and then I can connect a wire or a crocodile clip to the top of that. The track to the left, the mark there, is a cut in the track. This isolates the existing trace that goes to the emitter circuit. It is fairly long and can introduce instability, and I cut that, and the R1 resistor goes from the right hand side up to the emitter track between the device and the where the cut is. From the middle pin where the collector would go in for a normal device, I fit a series RC network. In my case, I used a 100 ohm and a 4.7 picofarad in series to deck. I used 0805 components. Just above the existing device, I cleared the green protective coating off, and the device, the BFQ19, was soldered to that land. The next picture shows the emitter resistor rotated round so it's connected to the device, and just to the left of that is the resistor and capacitor network to ground. The following picture is another view of it, with the resistor in the background and the series network from the collector to ground. I had previously set the spectrum analyzer and tracking generator for -10 dBm output into the 10 dB attenuator, then into the amplifier. The trace shown is the gain response from 0 to 100 megahertz. The gain at 4 megahertz is 9.3 dB. The gain at 14 megahertz is about 9.2, and the gain at 28 megahertz is approximately 8.8 to 9 dB. The response is fairly flat up to 100 megahertz. The table shown at the bottom of the screen is the amplitude or the gain of the amplifier, and I will use those figures for the noise figure tests later. This is the return loss image. This is measuring the output return loss. It is fairly flat from DC to 30 megahertz, approximately 24 dB return loss. The part of this return loss is due to the 5 dB attenuator on the output. When the signal goes into the attenuator and returns out, there is two lots of 5 dB, so 10 dB attenuation due to the output attenuator. I will now activate the relay and we will look at the input return loss. This is the input return loss. So this is approximately better than 20 dB up to 20 megs and about 17 dB at 28 megs, which is more than adequate. This is the setup for measuring the intermodulation. The tones are 0 dBm and the intermodulation is approximately 60 dB below that. If you divide the 60 dB difference by 2, you get 30. 30 dB above 0 dBm is plus 30. The intercept point at the device will be plus 35 due to the extra 5 dB attenuation. I will now set the frequency to 14 megahertz and repeat the test. The result is very similar at 14 megahertz. The intermodulation is approximately 60 dB below the two tones. I will repeat the test at 28 megahertz. The intermodulation at 28 megahertz is approximately 55 dB down, so the OIP3 has reduced a couple of dB. It is quite common for the intermodulation performance to not be flat across the frequency range of the amplifier. The next test that we'll be doing will be the noise figure. This is the noise figure at 28 megs, approximately 3 dB. Again, a good result. I also checked it at 4 megs and also 3 dB. So the noise figure is fairly flat across the band.